Okay, then tell me what is inductive effect, what is hyperconjugation, and what is resonance, right? So let us talk about it for a few minutes, then we move on. So start
Inductive
with, hmm,
inductive effect is like you'll have to shift the electrons towards the sigma bond. It's because like they have difference in their electronegative of that particular atom,
okay, great.
and it's like the one or the group which is more electronegative, it will shift towards the electron will automatically move towards itself.
Mm-hmm. Okay, great, great, great. So you are right. Now a question for you is, suppose if I have this is a carbon with a positive charge, right? Can you tell me this is going to act as a plus I or minus I? This methyl group in this specific case, is it going to act as a plus I or minus I? First of all, like, can you tell me what is plus I effect and what is minus I effect?
Plus, minus I is like that the electronegative group, it will be pulling itself towards it.
Mhm, mhm.
And plus I is like the electron will shift towards the
We can say
positive.
something like this, electron withdrawing. This is withdrawing the electron from our compound or species basically.
Electron giving and electron donating, please.
This is electron donating, right? So here what we can see that this methyl group is donating the electron density towards this carbocation. This carbon is having deficiency of electron, and this methyl group is trying to decrease that electron deficiency by donating some of its own as from the plus I effect, right? This is your plus I, and if I talk about minus I effect, if I have this, I have attached the chlorine. So this chlorine is acting as minus I, electron withdrawing group. It is pulling the electron density from my carbon. Okay, is this clear?
Yes, sir. So 1 minute, I need to change my network.
Okay, sure.
Sir, am I audible?
So you are audible. Okay. So can you tell me what is hyperconjugation now?
Hyperconjugation is like when the electron, like if there's a bond in that, the electron will
Okay. If we put it simply, you can say hyperconjugation is similar to my inductive effect. It is basically trying to stabilize our molecule by either donating electron density or by pulling electron density, depending on case to case. What is important here? Here we have to see the alpha hydrogen. What are alpha hydrogens? Alpha hydrogens are those hydrogens which are connected to the carbon, which is alpha carbon. Alpha carbon is the one which is directly the next carbon to the positive charge. The more the alpha hydrogens, the more will be the hyperconjugation and more will be your compound getting stabilized. All right.
yes, sir.
Okay. So what is the last one?
um mesomeric effect.
Yes. What is mesomeric effect?
Mesomeric effect is like
Hmm.
it delocalizes the electron like plus I and I mean plus M and minus M.
Very good. Very good. So can you tell me this thing? I have a benzene ring. Okay. Remember, this is my benzene ring, right? and I have attached a NH2 group here, and again the same benzene ring, but I have now attached a NO2 group here. Can you tell me which one is going to act as a minus M and which one is going to act as a plus M effect? And before that, you have to tell me whether this is a case of mesomeric effect or not. And if it is mesomeric effect, then how?
They both are the case of mesomeric effect. One is they give electron, and the other one it's like they withdraw the electron from the benzene ring,
Okay, okay, great. So if it is donating the electron density, how it is going to do? It is going to supply its lone pair inside the ring, right?
and it become a double bond.
Yes, good, good, good. And here what you will observe, this is like this. And as my oxygen is more electronegative than my nitrogen, it will
The
pull the electron
charge,
density from the ring.
yes,
Yes. One thing that I would like to add here to identify to make things easy when we are going to say a group is acting at a plus M effect or if it is acting as a minus M effect. So we can simply see. Suppose this is my conjugated system, a benzene, right? If I have an atom which is directly connected to this benzene and I have another atom which is next to this atom and it is more electronegative. Suppose out of carbon and oxygen, which one is more electronegative?
oxygen.
So in this case, when a conjugated system is attached to an atom, which is again attached to a more electronegative atom, in this case, you are going to observe minus M effect. On the other hand, if you have an atom which is directly attached to my benzene ring, a conjugated system, and next to it, another atom is attached, which is not more electronegative than this atom, then this is going to provide the electron density. It is going to act as a plus M effect. So the thing is, we have to see the atom which is next to the atom which is connected to a conjugated system. Is it making sense?
Yes, sir.
Okay. So this was like 11th class concept. So let us move ahead with our chapter and we are going to pick up a little bit of pace now. So we can cover it up. Right. I hope this question, we did this question or not? Chlorine is selective, chlorine is reactive and bromine is selective.
Yeah, we did this.
This is another NCRT question. This is based on your what we call isomers. Basically, it is asking like how if you are doing the chlorination of this compound, in which case you are going to get a single monochloride. So if you react this isomer, you can create several isomers from this single molecular formula, and you have to see all of them. If you have this one, if you react it with if you do the chlorination of it, if you are reacting it with Cl2 in presence of H mu, which is sunlight, you will get a single monochloride, right? And the second part is three isomeric monochloride. For three isomeric monochloride, you have to start with this one. If you attach chlorine here, you are going to get a unique structure, unique isomer. If you attach it here, unique. If you attach it here, unique. The rest, you will get the same answer. Suppose if I attach it at the first position, I get 1-chloropentane. If I do the same on second carbon, 2-chloropentane, 3-chloropentane. Right. So if I am reacting, if I am doing the chlorination of this specific isomer, I will get three possibilities. Is it making sense?
Yeah.
Okay. So you can attempt this question. This is very similar to the one we did previously. And if you still have doubts with this one, then you can let me know in the next class. Now, the third preparation method. Can you tell me the first two methods by which we have prepared haloalkanes? The first one was alcohols. We started with alcohols. We had 5 or 6 methods. Then we jump to the alkanes. From alcohols and alkanes, we have prepared haloalkanes. The third one, the third category is allylic halogenation. We will start with a allylic halogen. Oh, sorry, allylic compound basically. You know what is allylic position? Allylic position is the one which is connected to the sp2 carbon. This is my allylic position. The carbon which is next to a sp2 carbon is called an allylic carbon. Okay,
Yes,
this is
sir.
allylic position. Now, From this allylic compound, we can also prepare our haloalkanes. How we can do this? You can simply heat Br2 and you will get your allylic position. Basically, you will observe the addition of bromine at the allylic position. Simple. You have to do what? You have to add Br2 in presence of heat. This triangle is symbol of heat. Or what you can do? You can add this reagent. NBS or Br2 heat, both of them are going to do the same work. NBS is what? NBS is N-bromosuccinimide. This is we call N-bromosuccinimide. It is a reagent. It is a basically reagent by which we can form allylic halogen. This will simply add
Is it
bromine
like
on
a
the
catalyst?
uh, you are saying catalyst?
Yeah, is it like a catalyst? Like it involves, or
It involves. It is not a catalyst. It is a reagent. It is N-bromosuccinimide. And these two are different routes. This is different route. This is different route. But the product that we are getting is same.
yes,
Suppose suppose you have to make tea, right? You can either use Tata tea or you can use some other brand tea. But ultimately, what you are making? Tea, right? These
yes,
are different tea leaves. These are different brand tea leaves, but the product that you are getting is tea, right?
yes, sir.
Okay. You can do the same in presence of chlorine. You have to take Cl2 or alternative, what you can do? You can take NCS and chlorosuccinamide. And in both cases, the product that you are getting is going to be a allylic halogenated product. The halogen will simply get attached to the allylic position. Is it clear? You will see this type of reactions in your NCRT and I'm going to show you. So please see it, and if you have any doubt, then let me know. These are reagents.
Yes, sir.
Sure.
Yes, sir.
Now, a very important reaction now that I'm going to teach you. See, if you are using Br2, right? But now instead of heating it, you have done what? You have taken a non-polar solvent. You have taken a non-polar solvent like CCl4 or CS2. Why they are non-polar? Suppose if I am drawing the structure of CCl4, are we going to get a dipole moment here?
No,
The dipole moment is going to be 0 or not equal to 0.
zero.
Why?
So because it's fluorine attached to the carbon.
No, because we are observing equal and opposite dipole, a vector quantity. If two dipoles are acting in opposite direction, they will cancel each other out. I told you, right? Do you remember that exception? I told you CH3F have less dipole moment than CH3Cl because of the exceptionally long bond, basically. There I told you like the overall dipole moment will be calculated by seeing the entire vectors, all the vectors. Ringing any bells?
So
Are you sure this is clear why this molecule is a non-polar molecule? Because
I can say about CCl4.
this is CCl4.
No, you didn't say the exception that way. You
No, no
said that
exception. Hmm.
you said that you didn't say about this exception CCl4. You said that dipole moments will, if they're acting on the same direction, they'll add up, and in opposite direction, then cancel up.
Uh, so this is acting in opposite direction. If I go back to show you, uh, 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 see, I showed this. If the dipole moment are acting in opposite direction, the overall dipole moment will be 0. CCl4 is 0. CF4 will be 0. CBr4 will be 0. Okay,
Yes, sir.
please revise. Hmm, okay, now that's what. Now, if you are using a non-polar solvent, these are basically solvent and they are non-polar. Now, instead of heating Br2, you are using Br2 with CCl4 and CS2 or CS2 basically. You can use either one of these. Then you will get a different product. Now, you are not going to observe the allylic halogenation. Now, the halogen will simply add across the double bond. Here you have the double bond, right? A halogen will come and simply add like this, and this double bond will be removed. Why this double bond is getting removed? Because carbon cannot form more than 4 bonds. Is it making sense?
Yes.
I am going to ask you some questions on this specific topic, so you should be like, you should get clear. One more question for you. See, this molecule as a whole is non-polar, right? Because equal and opposite dipole cancel each other out. But what if I am talking about this specific bond? What if I am talking about this specific bond? Is it a polar or non-polar bond? A bond, not a molecule.
Polar.
The bond is polar, but as a whole molecule is non-polar because of cancelling.
Yes.
No. Let us move ahead. This is my question. Can you identify the allylic position in this compound? Which is allylic position?
The second position.
This one?
No, the other ones. But
This?
yeah.
Okay, because this is the position which is next to the sp2 carbon, and the allylic position itself should be sp3. So this is allylic position. What we are doing? N-bromosuccinimide or Br2 heat. So the product that we are going to get is simple halogenation at allylic position. Is it clear?
Yes.
Now, in this case, which is allylic position? This one?
Second position.
This one?
No,
No.
the one with the double bond, the opposite, like adjacent to it.
This one?
Sir, on the top, on the top.
This one?
Yeah.
Both of these are allylic position. Both of them are next to the sp2 carbon. Na?
Yes, sir.
So you can do bromination or chlorination. Here we are using chlorine at either of the position. You can add it here or here. The same thing you are going to get. Is it clear?
Yes,
Now
sir.
a question for you. A question for you. The same thing. The same thing. I am taking this compound, right? I am taking this compound. Now I am again taking bromine, Br2. But rather than heating, what I am doing, I am using a non-polar solvent. So what should be the product here?
Bromine will be formed on the ring.
Where?
Bromine will be formed on as a byproduct.
Not as a byproduct. I told you, na, whenever you are doing this thing like taking a non-polar environment, this is basically solvent. So the bromine will get attached across the double bond like this, and this double bond will be removed. So the product that you are going to get here is simple. The halogen will attach across the double bond. And you might be wondering why we have removed this double bond. Is there a question like this? Why we remove this double bond?
Yes, sir.
Okay, so if I zoom it in, if I zoom this thoda sa, I am just zooming this part. We have a carbon here, right? CH, CH. There is a double bond. Now you have to tell me how many bonds this carbon is making. This carbon is making how many bonds?
Two,
Total. 1, 2, 3, and with this hydrogen as well,
four.
4 bonds, right? And
Yes,
similarly, this is making 4 bond as well, right?
yes.
Now, my question for you is, can carbon make more than 4 bonds?
No.
So if I am adding a bromine here and here as well, now how many bonds this carbon is holding?
Five each.
It is not possible. So it has to sacrifice this double bond, because if I'm adding the bromine there, it is going to take 5 bonds, and this is not possible. So we have to remove this double bond. Is it clear now?
Yes, sir.
Sure.
Yes.
Whenever you are observing a non-polar environment with Br2 or Cl2, you will simply add that bromine across the double bonds. That's it. Okay.
Yes.
Now, next thing is the fourth preparation method is from alkenes or alkynes. Now your starting material is going to be alkenes or alkynes. And again, what is our priority? We have to prepare haloalkanes, right? We have to
Yes.
add that halogen. So let us try to think what we can do. Is it a halogen? Sorry. It is an alkene or not?
Yes, it is.
Alkene. So have you heard about Markovnikov addition and anti-Markovnikov addition? If not,
Yes.
not okay, good. If you have heard about it, then very good. So now, if for like if you have to prepare haloalkanes from alkenes, the reagent that you are going to use is HX. It could be HCl, it could be HBr, right? So if you are simply adding HCl or HBr, then the product that you are getting is Markovnikov product. What does Markovnikov rule says? That your halogen will be attached to the carbon which is having less number of hydrogen in the double bonded state. If I zoom it in, if I zoom this thing in, what I can see? CH2, CH, CH3. Have I written it? Correctly?
Yes.
Now, can you tell me in this double bonded state, which carbon is having less number of hydrogen?
The second one
So, so if we are going by Markovnikov addition, my halogen will go at which place?
on the CH part.
Okay, so we will get this product. Is it clear?
Yes.
Markovnikov addition simply. Now, if I am adding peroxide, if with my HBr I am adding peroxide, then what I'm going to observe? Now I will observe anti-Markovnikov addition. So what does anti-Markovnikov rule says? It says the halogen will go at the carbon which is having more number of hydrogen. So in this case, which is having more number of hydrogen?
The third one. CH3.
No, in the double bonded state only,
CH2.
CH2. So it will add like this. You might be getting confused that I have added it here. So to avoid confusion, let me add it here. Now it is clear.
Yes.
So this is about Markovnikov addition and this is about anti-Markovnikov addition. Is there any problem with this?
Oh,
No. Now, if you are using X2, X2 could be Cl2 or Br2. And again, you have used a non-polar or inert solution, inert solvent basically. So what you are going to observe? Simple addition of halogen across the double bond. All right.
yes.
Are these three methods clear?
Yes.
Okay. So I have to tell you something like the actual concept as well about this. Before that, let us see some questions. Okay. So you have this simple C reaction. First of all, tell me what we are doing here. Have you seen this
Bromine.
type of reaction anywhere?
Yes.
Where?
In bromination with heat, we add bromine and heat to the ring.
Okay. We have started with and this is alkane, alkene, alkyne. What is this?
Alkane.
Alkane. And what we are doing? We are doing bromination in presence of sunlight, right? So
Yes.
what we have seen? We have seen we can prepare haloalkanes with the help of alkanes by doing free radical mechanism or basically halogenation in presence of sunlight or heat. Okay. Now you have to
Yes.
tell me where should I add this halogen? You have to keep in mind that my bromine is selective. Bromine will always prefer the position which is giving it the most stability. So you have to tell me, shall I add my bromine here, here, here? Where should I add my bromine?
CH3Br.
You are saying I should go like CH3Br, like this.
Yeah.
You have to think again. I told you bromine is selective. Bromine will prefer which position first,
Ortho.
not ortho. You have to think in terms of primary, secondary, and tertiary. Which position is more stable?
So the one on the left side.
You are saying this.
Yeah.
Again, you have to think more. This is a primary, secondary, or tertiary. Which carbon is this? This carbon is primary, secondary, or tertiary?
Tertiary.
Nope. See, if I zoom it in, how it is written. CH2. Here we have CH. Here we have CH2. So
Okay,
this
sir.
carbon is
Taking.
secondary, right?
Yeah.
Are we having any carbon which is tertiary?
No.
Again, think, see carefully. If you see this carbon, isn't it 3-degree carbon? The carbon is attached to 3 carbon directly, right?
Yes.
So the product is going to be this one. Isn't making sense? You have to think in terms of selectivity and reactivity. Because bromine is
Yes.
selective, it will always try to find the carbon which is more stable. In this case, the tertiary carbon, and will attack directly at it. 99% attack will occur at the 3-degree position. Let me change my question. Uh-huh.
Sir, in bromination, there's major and minor product, right?
Yes, but here you have to only write the major product. And if you talk in terms of minor product, the concentration of minor product for bromination is like 1%. The 99% is going to be the tertiary one. It is very selective.
Yes, sir.
Okay. Now let me change my question. Now rather than bromination, I am doing chlorination. So chlorination, chlorine is reactive or selective?
Reactor.
Reactive. So chlorine is not going to look for stability. It will attack at the carbon which is holding the maximum number of hydrogen. In this case, which carbon is having the maximum number of hydrogen?
CH2.
This one, 3 hydrogens, right?
Yeah.
So it will attack at this position and you will get the A product as major, right? Selectivity and reactivity you have to keep in mind.
Yes, sir.
Sure, clear?
Yes, sir.
Okay, so let us go back to the topics that we were discussing. Okay, now see, what I can say is most of your questions will go by this simple approach, Markovnikov addition and anti-Markovnikov addition. If you are using only HBr or HCl, do the Markovnikov. If you are using this peroxide, which HBr, if you are using HBr with peroxide, then do anti-Markovnikov addition. Right. Most of your questions will go by this simple approach. But if they are trying to confuse you, if you are trying, they are trying to trick you in the question, what they are going to do, they are going to complicate your starting material. And then you have to think in terms of actual mechanism, like what is happening inside the reaction. So generally, whenever we have HX, we go by Markovnikov addition. But what is the actual mechanism that is happening inside this? This is carbocation mechanism. So let me explain you what I'm trying to say. Right. So is it an alkene or not?
It is an alkene.
Okay. I am reacting it with HBr.
Yes, sir.
So ideally, if you go by the simple traditional way, you are reacting it with simple HBr. So what products you should get? The Markovnikov product, right?
Yes, sir.
So the as per Markovnikov rule, your bromine will go at which position? At this position or this position?
The one on the
This is one,
downside.
this is two.
Two.
Two. Okay. As per Markovnikov, you will simply create this product and you will say this is your answer, right? As per Markovnikov, right?
Yes, sir.
But this is not the major product. This is the minor product. Why? Let us try to think about it. Whenever something is attacking at some place, what it would prefer? It would prefer stability, right?
Yes, sir.
Now, we have to think in terms of stability. HBr is an acid. We have talked about it. HCl, HI, HBr, HF, all of them are acids. What is the main purpose of an acid?
To donate H plus.
To donate H positive, right? The easier it
Yes.
is donating H positive, the more better the acid it is. Now, if I'm adding HBr, what its main goal? Its main goal is to provide H positive, right? Now, again,
Yes.
this is a double bond, pi bond, right?
Yes.
And pi bond can delocalize, pi bond can move around, right? So if you don't have to show it in your exam, this is just for your understanding. My pi bond has some electron density. How it has some electron density? See, I can uh like move my pi bond on the right hand side. If I am moving my pi bond on the right hand side, it will bear a positive negative charge here. These two
Yes.
electrons are going to go on this carbon, so it will have a negative charge, and consecutively this carbon will have a positive charge or not.
It will.
And what else I can do? I can move my double bond on the left hand side. I am showing you all the possibilities. So then this will have a negative charge, this will have a positive charge. Now a question for you. This is a 2-degree carbocation and this is a 1-degree carbocation. Which one is more stable?
2 degree carbocation.
2-degree carbocation. So the attack will occur from where? The attack will occur from this possibility. The attack will occur from here, right? So this double bond will pick up this H positive from this carbon, and consecutively we will observe a 2-degree carbocation, right? The positive charge will be developed on the 2-degree carbocation. Is it clear till
Yes.
this point?
Yes.
Yeah. Now, if we go by the Marconic of addition, then my bromine will simply come and attack at this site and I will get my product, right?
Yes,
But
sir.
if we go by the carbocation method, then what we can see? We can see a possibility of getting even more stable carbocation. How we can do that? At this position. At this position, what do I have? I have a hydrogen, right? At this carbon,
Yes.
I have a hydrogen. If I shift that hydrogen at this place, the positive charge will be transferred from this to this. If I am doing the hydride shift, I am getting even more stable carbocation, which is a 3-degree carbocation. And now my bromine can attack at this place as well. So I will get this. So the major product is going to be the one which is from the 3-degree carbocation,
Sir,
right?
isn't it like resonance?
Sorry.
Isn't it like resonance?
Resonance, like thoda bahut we can say like it is resembling the resonance, but it is not the same. You are saying like we have just transferred the positive charge from one place to another, right? Like the way
Yeah.
we did in resonance. It is
Yeah.
similar to that, but it is not the same. We are shifting the hydrogen here. Resonance is uh, basically specified when we are talking in terms of delocalization of charges. But here we are shifting the hydride. Okay, this is similar to
Yes.
resonance. You can relate it with that as well.
Yes.
So luckily, what you can observe, most of your question will go by the simple Marconic of addition approach. But if you have a substrate which is a little bit like complex like this one, where you have more than one site, here we have a 3-degree carbocation as well, na? So you will prefer the more stable one. Is it making sense, or shall I do something like a different approach? Hence, not always Marconic of addition. The actual way or actual approach is carbocation mechanism. Please look at this reaction for a few minutes. And can we like extend this class for 15 to 20 minutes?
Sir, I need to go out from my several government works over here.
Okay, you have to
Like,
go out.
actually, I
So
leave the class 15 minutes before the actual ending time.
you have to go before 15 minutes.
Yeah, sir.
Are you not in a mood to complete the syllabus? Like, now we have a lot of syllabus to cover.
Yes, sir. But then I need to give the details tomorrow. So I
Okay,
have
but
to go now.
from the next time, don't miss any class. Okay, I have to arrange an extra class for you.
So the extra class can be arranged on Thursday.
On Thursday, let me think. What do I have on Thursday? Monday, Tuesday, Wednesday. Thursday, I have a class with another student. We can do on Wednesday if you are free.
Wednesday I have two classes.
You have two classes. Okay. On Monday, I'm not free. The thing is Wednesday. I am free on Friday then.
So Friday, could it be like 1 hour class?
See, we have to like at least 1.5 hour. Otherwise, we won't be able to cover it.
Because
See,
Friday
if
we
you,
have Quran class.
see, you can do one thing now. Like you have to, you can ask me to schedule the class a bit early, like 7:30 or 7.
Yes, sir, I'm fine with that.
Okay, okay. We will talk about it after the class. Let us talk about the concept. Okay. Is this clear?
Yes, sir.
Sure.
Yes,
Are you making your own notes?
yes.
Because you have to write these mechanisms to understand them. Okay. So let us
So
move ahead.
like
Huh?
alcohol, like from the next chapter onwards, can I note down from the class itself? Because if I note it down, I'll be able to study and finish it within that time itself.
We will do that. But for now, as the first
Like
chapter is a
after
bit
this
lengthy because
chapter.
we have to cover all the concepts here. From the next ones, we will be only applying all these concepts. We won't be going into
Yes.
that much depth.
Like after this, can I be able to write in the class and finish it off so that I'll be studying after the
Sure, sure,
class?
sure, sure. I will be like opting. I will go by the short notes in the from the next chapter. Now we will have like
Yes,
10 to 15 pages, and we just have to do that.
yes,
Okay. For now, just you after the class, note it down, whatever we are studying now. For a few days, you will find it hard, but you have to do it. No other options. Okay,
yes, sir.
luckily, you don't have to do the free radical mechanism. There is not a single chance that they are going to give you this. So, what you can understand simply, whenever you have HBr with peroxide, you will create what? Anti-Marconi product. That's it. HBr with peroxide create anti-Marconi product. That's it. You don't have to go into the mechanism for this one, right?
Sir.
And one more thing that I would like to add here is only HBr show Kharash effect. What is Kharash effect? Kharash effect is anti-Marconi product. So if you are using, suppose, let us say, if you are using HCl with ROR, you are not going to get anti-Marconi product. Only with HBr, you are going to get anti-Marconi product. Apart from it, you are going to get the simple Marconi addition product. Is it making sense?
Yeah.
Only if you are having this combination, then you are going to get the anti-Marconi product. Otherwise, nothing. Okay.
Yes, sir.
If somebody is asking you, suppose in your Viva, they are asking you what is the reason behind it. So you can say the first and second step in the free radical mechanism, both are exothermic. Just say this is sufficient.
Yes,
Now, alkynes, if you have alkynes, what you have to do? Just double the equivalent. Rather than taking one, you have to take two, and the same thing you are going to get, right?
yes, sir.
Now, we have done this question, and we have few more questions. Okay, then we will go to the chemical reaction. Right. So let us do this. So try to understand this question first. What we have to prepare? We have to prepare 2,2-dichloropentane. What we have to prepare?
Formal to the fluoropentane.
Okay. So you know now how to convert the IUPAC name into the structure.
Yes,
You have to create pentane, and at two position you have to put two chlorine.
yes,
So you have these four approaches. You have to select the best one. The answer is written. I am going to show you the all the possibilities, like what can happen. So let us start one by one. Okay. Just see this for few seconds, and we have to apply this just now. You have to see this and tell me what should be the case. Isn't it similar to the this one? If I go back, I have an alkyne, right? And I am doing what? Addition of Cl2,
fluorination.
chlorination. So what I am going to get? CH2, 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 C,
Yes,
double bond, CH. And at which position should I add? At
on the second. Yeah,
this one, right?
Yes.
Is it the
One
product
more.
that I'm hoping to get? Is this the same product?
No.
No. So the first approach is not correct. Okay, let us think about the second one. What is this? This is hydrogen. So what we are going to do basically? Addition of hydrogen.
Hi.
If I add hydrogen and hydrogen here, this will convert from alkyne to what?
Alkene.
Alkene. Good. CH double bond CH2. Now what I am doing? I am adding
No.
2 equivalent of HCl. So what should be the product here?
It will break one more bond and then HCl will go and add to the second carbon. And
Okay.
Cl will go and get added to the second carbon.
Okay, let us see. Like this.
Yeah.
Is this the product that we are hoping for?
No.
Okay, just give me 1 second. I'll be back. Meanwhile, let's see this. What is this? And see this, and then see this. Are they not similar?
They are.
If I'm doing HBr, so what I'm going to get? I am going to get a doubly halogenated product at the carbon, which is having less number of, basically at this position. So I'm going to explain that. Just give me a second now.
Yes.
Yeah. Mm, okay. Okay, we did something. Okay. Cl2, the Cl2 will add simply at this position. Now at the third case, what we are going to observe? CH3, CH2, CH2, triple bond CH, 2 equivalent of HCl, right? So if I'm adding 2 equivalent of HCl, what I'm going to get? These, see, let us go
Uh,
by one by one.
double bond.
This Cl will like this, and this, let me do the entire thing, okay? If I have HCl, right? HCl will be dissociated in what form? H positive and Cl negative.
Mm,
Is it clear what I just did?
yes.
What I have told you that if I have a pi bond, what I can do, I can delocalize it. So
Yes.
I can do a attack from this double bond and I can pick this hydrogen. If I am doing this,
Break it.
it is going like this. See, first it will go here, negative and positive. Then it will pick the hydrogen from here. The direct method is to simply show the double bond is going to attack. Double
Yes.
bond CH2. Positive will be here, right?
Yes.
Now we have a negative charge. It is going to act as a nucleophile or an electrophile, this chlorine.
Nucleophile.
It will attack like this, and you will get Cl double bond CH2. Okay. If we have given one equivalent only, then our reaction will stop here. But how many equivalents do we have?
Two.
So the same reaction will occur one more time. H positive plus Cl negative. This double bond will pick that H positive, and by doing it, CH3, CH2, CH2, Cl positive will be here. And now it is going to become into single bond because it is going to attack like this. The pi bond will shift on the right carbon, consecutively the positive charge on the left one, and it will pick the proton from the carbon, basically this carbon, and it will convert from CH2 to CH3. Now, in my reaction again, I have what? One equivalent of chlorine left, and I will get my product. Is it my desired product or not? Can you
Yes,
can you name this compound? Can you name this compound?
two comma two dichloropentane.
Simple.
Yes,
Okay. Now this is the last case. You have to tell me what product you are expecting here. Let me draw it.
the
CH2.
bond will be broken.
Either it is going to be it is going to attack here or here. Which carbon you are expecting it to attack?
A,
A. Why?
because the bond will be broken and then the fluorine will go and attach to the least side.
Okay. So your answer is correct, but let me see whether you apply the same approach or not. First, this double bond will shift here, right? Negative charge and positive charge. This double bond is removed. This will pick this hydrogen, and what will happen? This will convert into CH2 and like this, right? And now
Yes.
this Cl will attack here. Now the question is, why we are attacking at this carbon? Why not this? Because both of them are secondary carbon. Because here I have CH3, CH2, and here I have only CH3. If I put a positive charge here, out of CH3, CH2, and CH3, which one will provide better inductive effect?
CH3CH2.
So you can like think about that way, also, right? समझ आ गया? Is it clear?
Yes, sir.
Please solve this question on your own. Otherwise, like it will help you to develop the methodology. Okay. Now we are done with the preparation of alcohols. Sorry, we are done with the preparation of haloalkanes. Now we are going to react these haloalkanes that we have prepared with some other material, and we will try to get something else. Now we have prepared our tea, and now we are going to add some different kind of masalas, or we are going to perform some other experiments to convert this tea into something else, right? What we call this part? Chemical reaction of alkyl halide. Before this, we are preparing alkyl halides, and now we have prepared those alkyl halides, and we are trying to convert them into something else by performing different chemical reactions. Is it clear?
Yes, sir.
Now, very important reaction, Finkelstein reaction. They might directly ask you what is Finkelstein reaction, explain. Simply, they will simply tell you Finkelstein explanation, explain what is Finkelstein reaction. So let us try to understand it. Okay. So what is Finkelstein reaction? Can you please read this for me? Are you able to understand my writing?
Yes.
So tell me what is written here.
To get alkyl iodide as the product,
Hmm.
they react alkyl fluorides or bromides with sodium iodide. Yeah,
Okay, good.
sodium iodide in dry acetone. They get alkyl iodides and a compound with Na, either it is Cl or Br.
Okay, so I think you have paid attention in your school class while they were discussing this topic, right?
Yes.
Okay. So this is basically a reaction where you are preparing alkyl iodides, right? By reacting alkyl chlorides or bromides with NaOI in presence of diacetone, right? So this is called Finkelstein reaction. This is a forward direction reaction because the side product that you are getting here is NaCl or NaBr, and NaCl and NaBr precipitate out. So this thing is getting precipitate out. So your overall reaction is shifting towards the forward direction as per Le-Chatelier principle. Okay. The
Yes.
question they might ask you from this topic is why we are using dry acetone. And this is a simple SN2 reaction. What is SN2 reaction? Can you tell me? Simple attack from the backside and the substitution of leaving group. One step reaction, Walden inversion. Okay.
Yes, sir.
Now you can use either NaI or Ki. The question is why dry acetone? So the answer is written over here again. Acetone is used because NaI or Ki are soluble in acetone. That means it will be in ionic form in acetone. Suppose whenever if you are trying to attack if you are trying to attach this iodine at your substrate, in which state will it act as a nucleophile? In ionic state, right? If it is in ionic state, if it is aqueous state, it can act as a nucleophile.
Yes, sir.
So in acetone, your NaI and Ki will be present in ionic form because acetone can dissociate your NaI or Ki. This is the reason they are attacking in the reaction, because if your I is not in the ionic form, it cannot act as a nucleophile. It should be in I negative form to attack.
Yes, sir.
But NaBr and NaCl in product are not soluble in acetone. The product that you are forming here, which is NaCl or NaBr, they are not soluble in acetone. If they are not soluble in acetone, they will not dissociate in acetone and they will simply precipitate out in your reaction. They will form solid clusters and they will precipitate at the bottom of your beaker or your container. So ultimately, what we can say, they are not participating in the reaction. This
Yes,
NaCl or NaBr is in solid form. This is not in ionic form. Hence, this Cl negative cannot further create hindrance in our reaction. It will stay at the bottom of it in the solid form. So we are not getting any other product. Okay, let us compare. NaBr in product are not soluble in acetone. They won't attack further in the reaction and simply get precipitated. Why dry acetone? Cause if H2O is used, it will cause hindrance in the reaction by behaving as a nucleophile. It might produce alcohols. Why we are using dry acetone? Because if you are using aqueous acetone, see, whenever you are seeing this dry thing now, this dry means you are avoiding any chance of getting H2O. Dry means you are eliminating H2O entirely. Okay,
yes, sir.
dry acetone means no H2O. And we have already studied that H2O can also act as what? Have I told you what is a nucleophile and what is a electrophile?
Yes.
What is a nucleophile? Nucleophile is something which has some electron pair to donate. H2O has electron pairs, lone pair basically.
Yeah.
So H2O can act as a nucleophile. So to avoid that possibility, so that we can specifically made attack from the iodine, we are using dry condition. I hope it is making sense.
Yes, sir.
Okay. Please take few minutes. This is a very important reaction. Look at this entire thing. I hope this part was clear because you yourself told me what is this. Just look at this, and if you have any doubts, then let me know. Is it making sense?
So 1 second. Done, sir.
Okay. Now, Schwarz reaction. Let us see whether you are able to answer this as well or not. What is Schwarz reaction?
It's basically like preparing to
Hmm.
get the product as alkyl fluorides, like
Good.
reacting alkyl fluoride or bromide in the presence of metallic fluorides like AgF, uh, AgF
You
to
can learn
form.
any one of, like any two of them. You don't have to learn all of them.
Yeah, it's like we to get alkyl fluorides, we react AgF, um,
Mhm.
AgF to prepare alkyl fluorides and get Ag, whatever the component we use, Br in the
Ah, simple.
alkyl.
Simply like from you have to replace Br by chlorine and AgF will be converted into AgBr. Simple.
Yeah,
Right. Now,
yes,
why we are using a special name reaction to get this alkyl fluorides? The reason is fluorination is very reactive and exothermic. So to do fluorination, you have to first of all need some specific conditions, right? You have to be very careful around it. And because of this, you have this special reaction, Schwarz reaction. Like they might ask you why, like we are preparing chlorinated haloalkanes, brominated haloalkanes by simple methods. Why we need this Schwarz reaction specially? Because it is very like hard to handle fluorine because it is very reactive. So we have this special method. By this special method, we can prepare uh, alkyl fluorides by like without any what I should say harsh consequences. Okay.
yes, sir.
Okay. Now you have to solve some questions, and I will mark some questions as well from your NCERT. Okay. Now, first of all, identify. Have we seen this type of reaction?
Yes, sir. Bromination.
Bromination. What is special about here? What is special here?
Here they use PPL4, which is an inert solvent.
Very good. So what you are going to get?
I'll get
Simple
bromine
addition
on
of
both the
bromine across
sides. Yeah.
double bond across simple, right?
Yes.
And what you have to keep in mind that to do this reaction, you need alkene. Simple सी बात, ठीक है? Now,
Yes, sir.
if I see this, where have we seen this reaction? What is this N-bromosuccinimide? This is NBS basically. Where have we seen this?
Bromination. Bromination.
Bromination at what, like, what was the substrate while we will be discussing this? What was the topic? Like, what was
Bromine
the substrate?
formed on the place of double bond.
You are saying I should add it here.
Yes.
No, see, if you have this PDF image,
On the molar hydrogen side.
this one,
Yeah.
nope. See, while I was teaching you this N-bromination, N-bromosuccinimide, or I have told you na, PC, we can use Br2 or heat or NBS. Both of them are going to give you the same product. And for this, if you have allylic position, we talked about na allylic halogenation. Do you remember
Yes, sir.
allylic halogenation? So this is sp2 carbon, and to this sp2 carbon, I have a carbon which is directly attached to it and is sp3 carbon. So this is my allylic position. So if I'm using NBS, NCS, or Br2 heat or Cl2 heat, then I'm going to get allylic halogenated product. What I'm going to get? Allylic halogenated product, and my double bond is going to remain as it is. This is very important. You have to learn to differentiate between different sort of methods. You have to learn the reagents for that.
Yes, sir.
Is it clear?
Yes, sir.
Okay, okay. Now, this is PBr3. Have we seen PBr3 before?
Okay. Still with
A reaction
alcohol.
where sorry. Come again.
A reaction with alkenes.
Alkenes, no.
Alkenes.
Nope, not alkenes.
PCl5.
PCl5, PBr3, we did these type of reaction with alcohols, right? The starting reagent was alcohol. If you react alcohol with PBr3, you will get a halogenated compound. Remember? SN2 mechanism we did.
Yes, sir.
So here, although we have seen BBr3 getting used to convert alkyl halides, but for to work PBr3, we need alcohol. We have not seen any reaction where we were reacting our alkene with PBr3. So this reaction is not going to proceed. We are not going to get anything. Okay.
Yes, sir.
Okay. Now, have you seen this type of reaction anywhere? The last one.
Einstein's reaction.
Which one?
Einstein's reaction. Means.
See, you got confused now. In Finkelstein, what we were using?
Oh,
NaI
yes,
or Ki.
alkyl iodide.
See, acetone is not able to dissociate it. In acetone, NaBr will exist as NaBr solid. It is just simply existing at the bottom of your container in solid form, precipitated, right? To do a reaction, what do you need? You need ions. Ions are going to act as nucleophile or electrophile, right? So acetone is not able to dissociate it. It is not able to convert this into Na positive and Br negative. So you are not going to get any nucleophile in your reaction. So this reaction is not going to occur,
Proceed.
proceed. NaBr is already precipitated. It is not in its ionic form. Simple, clear?
Yes.
Okay. So these are the questions from your NCRT, and I think you have seen the answer. So let us twist it. Can you tell me the name of this reaction? What we call this method? When you are reacting alcohol with SOCl2, what we call the name? Like, what is the name of this reaction, basically, simply? And also tell me the product. What should be the product here?
This Cl2 will be on, and
Sorry?
SO2. Cl2 will be on the benzene ring, and SO2 will be the byproduct.
No. Do you have the notes? I have told you, no? There is this method we call Darson method, and this is
Method.
special because the byproducts are in gaseous form, so you don't have to separate them out. They will simply evaporate.
It
See,
will become the Cl will be there, and then SO2 in gas and HCl in gas.
see, simple. Okay.
Yes.
What about this one? Now you have to think carefully for this one. What should be the product? What you are doing? You are having Br2, okay, and you are heating it or sunlight basically. So what should be the case? What you should do here? You have two
Bromine will
possibilities.
be formed
Bromination will occur, okay. At which position?
on the allylic position, that is on the double bond side.
I am giving you two options, A or B.
D.
Which B, right?
Yeah.
Why? Because when I have Br2 and heat, I will prefer allylic position halogenation. This is my allylic position, right?
Yes, sir.
And my product will form like this. I hope now the things are connecting.
Yes, sir.
And you might be wondering, like, why not attacking here?
So
There
because
are some chances that this will attack at that position, but that is not going to be your major product. Some concentration is going to be in the form of, like, some of the product you can see like this. Sum of the product. See, sum of the product you might see being into this state, but this is very small, like 1%, because my bromine is also selective. So the chances of getting this is very low. Is it clear? Clear? The major product is going to
Yes.
be this one. Okay, now the last one. See this one and tell me what you should do here. You have two sides. The most, what you can say, the prone sides where you can do the attack are this one, or are you able to see any other side?
It will be Markovnikov's addition.
Which one?
Markovnikov's addition.
Think again. For Markovnikov addition, what do you need? An alkene, right? Although
Yes.
you have an alkene, but this is an aromatic alkene. And whenever you have a aromatic site won't uh, prefer to lose its aromaticity. So whenever something is in its aromatic state, they will try to avoid any sort of attack. So this is very stable. This ring is very stable, so it will avoid any attack. So this ring is not going to participate in the traditional Markovnikov rule. Markovnikov wala simple. So Tara. Now you have to think again. You have alcohol, right? And we have seen some reaction, like we have reacted HCl to get haloalkanes. Okay. Have I
If you guys
gave
will go
you
ahead and get attached to the CH2 pump.
simple like this?
Yes.
Now, a question for you, like, have I given you the homework? Have I marked aromaticity as well in your homework?
No.
So you have another homework.
Work from last class.
Like in this class, I'm giving you another homework. You have to see थोड़ा बहुत about aromaticity, Haskell rule. ठीक है? Go through these two topics before the next class, and it will help you to understand. Your question was valid. We have a alkene here, and we have seen like if we are reacting HCl, we can do the Markovnikov addition product. We might get something like this, right? There should be a possibility of that, right? Why this is not happening? So for this, I would request you to see thoda bahut about a little bit about aromaticity and Haskell rule before the next class, and I will explain you in the next classes. Okay.
Yes.
Now, okay, we have this simple question. Can you tell me the product here?
So can I leave the class after this question?
Sure, sure. Let us do this question first.
Yes, sir.
Hmm.
The alkyl iodide will be formed. No.
Okay, yes, alkyl iodide will be formed, but at which position?
On
1 degree. You are saying something like this should be formed, right?
yes.
See, this is wrong.
Since the double bond is there, it will not be formed.
Hmm. So what else we can do here? What we know that this HI is simply acid. What is the main purpose of an acid?
Give H plus.
And H plus is basically having electron deficiency. So to like provide some electrons, we will look for a site where we are having some electron richness. So we can say that this what I should say this double bond can attack because double bond is having some electron density. How it is going to attack? It will go here first. Negative charge will be developed here. Positive charge will be developed here. This negative charge will pick this hydrogen. Okay, this hydrogen will go here. Now, what is the benefit of doing this? We have converted alkene into what? Alkane. Now,
So why is iodide not formed?
see. This is your iodide. Now, this positive charge has developed here. And after doing the protonation, my iodine can attack at this site or not?
It can.
So we will get the major product as this.
Yes, sir.
Clear?
Yes.
Now, this one, you should be able to answer this. A very simple question.
So it's CH3, CH2, I plus NaBr.
हाँ ठीक है, single chain reaction, right?
Yes, sir.
This one,
Bromine will be attached from the top part.
what we call this?
Bromination.
Which type of bromination?
I didn't get your question, sir.
Which type of bromination? Which position is this? What we call
Second.
this position? Allylic position, na? Allylic
Yeah,
bromination is also. Okay. And if I'm doing this, what should be the product?
bromine will be.
Bromine will add across the double bond. Simple, right?
Yes.
Okay. So we have few more questions, but okay, we will discuss this in the next class. That means tomorrow. But before tomorrow's class, you have two homeworks. You have to read about
Yes.
aromaticity, and you have to do the questions till this page. You have to do all